Hello friends, myself Nikhil Doy. I'm final year undergrad pursuing my degree in electrical engineering at IIT Tirupati. Today I'll be presenting my technical paper presentation on multimodal learning for clinical decision support and clinical image-based procedures for this year. And the paper is Automatic Breast Lesion Classification by Joint Analysis of Mammography and Ultrasound. This paper is written by our authors Gabriel Habib, Nahum Kiryati, and many others, as mentioned in the slides. These people are from School of Electrical Engineering at Tel Aviv University in Israel. So let me give you a brief introduction about what the problem statement is. Classification of breast lesions is a challenging task for radiologists. Malignant and benign lesions can be differentiated by their shape, boundary, and texture. Usually, mammography is better at detecting the boundaries, whereas ultrasounds are better at detecting the texture. So these are basic things, but also the usually malignant regions have irregular and not well-defined boundaries, as they have the ability to spread. And the ultrasound imaging has proven to be a valuable tool in dense breast, whereas the solid tumors can easily be detected through mammography. So here, authors have come together and built a deep learning model to classify whether the breast cancer lesion is malignant or benign using mammography and ultrasound scans both. So let's take a look at the data set. Here, there's no public library as public data set, so they have created their own data set in which there are 153 biopsy-proven lesions, in which 73 are malignant and rest 80 are benign. As you can see in the image, on the left-hand side, it's a mammography, and on the right-hand side, it's ultrasound, and the segmented out portion is the malignant region from both both the modalities. So the authors have provided us with two model architectures. Number one is a single modality. Here they have given two convolutional neural networks, one for each modality. Here the contoured lesions were cropped into image patches and submitted to geometric transformation like translation, rotation, and flipping to augment the dataset and generate additional input. This input will go through this convolutional neural network, and in the end, it will give us the uh, probability of this lesion being benign, this lesion being malignant. Next, and the next model architecture provided by the authors is a multi-model network. Here, the high-level perceptual descriptors of matched lesions were extracted from both trained single modality networks and combined by concatenation. Later on, using the fully connected layers, uh, they have extracted a high-level feature of this concatenated high-level descriptor, and then softmax layer has given the probability of being malignant or not. So let's take a look at the loss function and the training. So we have used two loss functions. One is binary cross entropy, another is large margin cosine loss. We have used binary cross entropy, as mathematically it is a preferred loss function under the inference framework of maximum likelihood. So in short, it will calculate a score that summarizes the average difference between the actual and predicted probability distribution for the predicting class of malignant. And whereas the second one, large margin cosine loss, which is commonly used in face recognition tasks. Uh, uh, Talking about this in this short video is not possible, to be honest, but I will just rephrase the words given by present in the technical paper, because mm, talking about this will take a lot of time. Mm. So LMCL defines a decision margin in the cosine space and learns discriminative features by maximizing interclass and minimizing intraclass cosine margin. Also, the image below is the way we are going to train. Authors have provided with us two training methods. One is let the complete training. Uh, yeah. So two methods. First one is single training, where the mammography model will go through CNN, will give us a vector, and then software will detect the corresponding modality score, and then this learned high level vector will get concatenated and then go through the fully connected network to give our multimodal score. This is one way of training. Other way of training is the end-to-end training. Here, both the modalities will go through their corresponding CNN, convolutional neural networks, and then the high-level feature vector will be concatenated and then go through the feature network to compute the multimodal score. So so the difference is that in the later in this end-to-end training module, this high-level vectors are not learned. They will be uh, uh, learning as this fully connected network is also being learned. So they are being learned simultaneously. So yeah, these are the two different ways of training. Next, let's take the look at the results. So here you can see that there are two different training methods, separate and end-to-end, and we have correspondingly two loss function, binary cross entropy and large margin cosine loss. And we have also trained on the two different modalities. One is the CNN and other is the transfer learning. We are using transfer learning because we know that total number of images are less. So when the data is less, we usually use transfer learning. And we have used the Google Net architecture for that. So the scores are given, and the scores are the AUC score, area under the curve, which is the area under the ROC curve. So the closer it is to 1, uh, the better our model is. Yeah, sorry. So the scores are there are 3 scores from mammography, ultrasound to combined. So yeah, here you can clearly see that the combined model has been better compared to all others in uh, any training method and loss function. Just it has degraded in the transfer learning one in the LMCL. This may be due because of the less number of images, cause LMCL uh, because of LMCL. I can't. Yeah, and because of the LMCL, let's move forward because talking about LMCL isn't possible right now. Mm. Yeah, and we can also see that transfer learning has worked better compared to our trained from scratch CNN. Uh, yeah, so combined and transfer learning is currently the best way to opt for. So, and yeah, later on, authors have worked with radiologists to check whether our model could be implemented uh, in um, in hospitals right now. So they have taken they have worked with four radiologists. Mm, they were given this mammograph. They were given this images of mammography and ultrasound scans, and to were asked to tell whether it is malignant or not. So we can see their AUC curve, AUC score, and the average of these four AUC score is 0.95, which is very close to our AUC of 0.942. So I must say that they have done this splendid work of comparing this of this comparison. Uh, Next, yeah, this major insights from the model. Uh, is this model paying attention to the same attributes as radiologists and predicting whether a lesion is malignant or not? So they have used this algorithm called gradient cam algorithm, where where it looks whether our uh, model is looking at the key features or key areas where the radiologist looks while predicting whether the lesion is malignant or not. So the hotter areas indicate attended regions. We observe that for malignant lesions, the model appears to rely significantly on the lesion boundaries, especially where irregular features are encountered. Thank you so much.